Screen share. So is
Yes.
this visible?
Yes, it is visible. Okay. So very good morning and welcome to our first lab sessions. Okay. That session will be given by Mr. Arko Dutta. He is a MTech student of Computer Science and Engineering Department of NIT Rourkela. And very warm welcome to Arko. And he is going to give his presentations on sensing and resource constant machine learnings and having some simulations and all those things. Okay, so it's on Arco. You can carry on the next sessions. Thank you.
Okay. Thank you, sir. Thank you for the warm introduction. And I guess my voice is audible.
Yes, you are properly audible.
Yes, sir.
Yes. So, good afternoon, everyone. Today, I'll be presenting a session on sensing and resource constrained machine learning. And we'll be doing some hands on devices, some hands on demonstrations. So, we'll go through what is sensing, and then we'll give a demo on sensor interfacing. Then we'll go for machine learning and its need for running on resource constrained devices. And finally, since I'm running on a backup machine, like if the primary machine is up, we can show how to harness the power of resource constraint machine learning in an intelligent, personalized air quality monitoring device. Else, I can show you the steps virtually. So first, let's start with some basics of sensing. And what comes to our mind when we think about sensing in a general term, not too much in technical term. What comes to our mind when we think about sensing?
When we observe something or feel something
Yes, basically the sense
from our
organs.
environment.
When it perceives some kind of information from the environment.
Yes. So basically our sense organs, right? We use our sense organs to perceive various factors from the environment. So as you can see, like for example, sight. Our sense organ is eyes, and our in a device, the same sight can be implemented using a camera. Sound, we can go for microphone. Smell is basically the perception of various gases, and so we can use a multi-channel gas sensor, which basically like measures the concentration of various gases around us. For touch, we have touch screen. Everybody has seen a touch screen. And for taste, taste sensors are still in research for a general purpose, but for specific purpose, there are some devices such as this. So if we come to a formal definition, we can say that sensors are devices which gather data of contextual information, that is what is going on around me, and it will provide an electrical signal based on it. So sensors may be using the principle of capacitance or the principle of resistance, and it will provide a voltage by using the formula either V equals to IR, where R is the resistance, or V equals to IC, where C is the capacitive resistance. So this electrical signal can be converted into bits and bytes, and these bits and bytes can be read as some like decoded as some data. So we'll move on with the demo on sensor interfacing. To assist me on my demo, I have Mr. Povitro Maji with me here. So first we will be setting some giving an intro, what is the language being used. We are using MicroPython. Now what is MicroPython? MicroPython is a subset of the language Python, which is specially designed for microcontrollers and embedded devices. This is because Python contains a lot of libraries, and this makes the size huge. But as you will see in further slides, we are restrained to a few megabytes or kilobytes. So we need if we want to code in Python, we can use a subset. And MicroPython is since Python is like a more English like, we can use MicroPython as for fast prototyping. The IDE we will be using is Thorny, which has a very like simple interface, and we can choose the interpreter easily. There are options. And in the sensor, in this session, we will be going for temperature sensor, dust particle sensor, multi-channel gas sensor, and OLED screen. So we'll be using two microcontrollers. The first is the Raspberry Pi Pico W, and the second is a Waveshare ESP32S3 Pico. Both cost around 800 to 1200 rupees. So it's like in the lower budget range. And let's see what features we have. In Raspberry Pi Pico W, we can see that we have an RP2040 microcontroller with dual ARM Cortex M0 cores, whereas in Waveshare ESP32S3 Pico, we have ESP32S3 microcontroller with a dual core processor here as well, which is a 32-bit Extensa LX7. In Raspberry Pi Pico W, our clock rate is 133 megahertz, and in ESP32S3 it is 240 megahertz. Flash memory also differs quite a lot. In Raspberry Pi Pico W, we have 2 megabytes flash memory. In ESP32S3, we have 16 megabytes flash memory. The SRAM in Pico W is 264 KB, whereas in ESP32S3 it is 512 KB. Also, we have got 384 KB of ROM and 2 MB of PSRAM, which is also known as SPI RAM. This is an external memory which is attached to the board, and we can use that for RAM as well. Apart from that, the Raspberry Pi and Pico, the like ESP32S3 Pico, both contain Wi-Fi and Bluetooth capabilities, and both can communicate using BLE technology as well as Wi-Fi in the 2.4 gigahertz range. However, in Raspberry Pi Pico W, we have USB Type B, whereas in ESP32S3, we can use USB Type C, which is nowadays it is more universal. So we'll go for temperature and humidity sensor first. So while Povitro is interfacing the device, which we will be showing, we can go to a little bit of theory here as well. So temperature and humidity sensor, so what it does is, let's first go for temperature sensor. There is a property of metals that based on the temperature, the resistance changes. So as we can see in platinum, the change is a constant with a positive slope. In copper, it is a bit of skewed, as is the case with nickel. Now, since platinum is quite expensive, we mostly use copper and nickel in our temperature and humidity sensors. And we can just measure the output voltage using that V equals to IR equation, and based on the resistance, like we can calculate the resistance from that, and based on that resistance, we can just drop an intercept towards the x-axis, and we'll get the temperature. Meanwhile, the relative humidity also affects the resistance, and the calculation principle is same. The relative humidity increases and the resistance decreases. So we'll be first interfacing a DHT22 sensor. So the DHT22 sensor is connected will be connected first to the Pico W with 0. with the 5 volt, like the VCC pin connected to the. Is it visible? Is the device visible?
Yes, it is visible.
Okay. So here, I don't think it will be quite clear from the camera, but the there is a minus, output, and a plus. The purple wire here is connected toward is a positive and is connected towards the VCC or V bus, which is providing a 5 volt output, and the white here is ground, which is connected towards the negative, and the output is connected toward to GPI of 4. So in this demo, we can see we'll be opening up our IDE, which is Thorny. MicroPython is loaded into this, right? Step double found. So we'll be first finding the port. Port is COM21. So as you can see, our Pico has been detected by the IDE. The wire is loose. Okay. Can you just hold it? Yeah, thank you. So, okay, just plug out and plug in to the other port. So, yeah, hold it.
Excuse me, sir.
Yes.
Sir, when you're interfacing this one to system, is there anything to be installed priorly?
Yes. First, in our computer, we should install an IDE called Thorny, and for MicroPython, there is an UF2 file, which is basically a file which should be flashed. Uh, what we have done prior to this is, if we search MicroPython plus our board's name, we can find a distribution of the file and as well as the installation instructions. So we need to just place this file, download this file, and place it in the bootloader. And the MicroPython files will be loaded. And then we can use Thorny to just code in Python, which will be seen here.
So simply connecting a USB from your Raspberry Pi to the system is enough, just like this Uno.
Yes.
Okay. So 5 volt supply is mandatory for the Raspberry Pi microcontroller also.
Yes.
Okay.
So,
Sir, this Thorny IDE is only available in Raspbian OS or for other OS also?
so it is available in your Windows as well as Linux.
Okay, thank you.
So as we can see that the temperature and humidity are being displayed on the screen, and what we can do is we can display this data via Thorny. For that, we need to change the formatting of the output a little bit. What we have to do is we have to just print it like temperature equal to, and without any spaces, and then we have to add a comma and the other value. And if we use this, there is a serial plotter inside it. 1 minute, we need to change the humidity values as well. So there is a serial plotter inside which will display the values being changed. In DHT22, there is one caveat, that is the delta between one reading and the other should be around 2 to 3 seconds, else it will provide the same reading, like it will not refresh. What we have observed. So as we can see, so what I'm doing is I'm holding the sensor so that there is something, some changes in the data. And as you can see, the blue one being the temperature and the orange one being the humidity. The temperature is slightly increasing, but humidity changes you can see properly. So in the code, what we have done is we have just the DHT is already available with the MicroPython, and the utype is a library which is MicroPython's version of time library of Python. What we are doing is we are instantiating the DHT22 class, which contains the driver for DHT22 sensor, and we are mentioning the data pin, and then we are just telling the sensor to measure in an infinite loop, and we are extracting the temperature and humidity and printing them, and then we are giving a delay of 300 milliseconds, 3000 milliseconds, which is 3 seconds. Shall I move on to the next demo, or is there any questions?
Yeah, I would
Why
like
the while
to.
loop is kept?
So that we can measure the temperature and humidity indefinitely. Like if we remove the while loop, it will just measure the data once, and then the program execution will be completed. So to keep on measuring the data, because for our IoT devices, we want to measure our data indefinitely, right?
Okay.
So we that's why we can keep it inside an infinite loop.
Actually, I'm not from engineering background, so there is a. It might sound a silly question. I would like to ask that whether this device will be all the time connected to a laptop or computer,
No,
because it is sensing
you
the.
can. We are using if shall I open it? Yeah, we are using a USB cable which is like type A to type B. So we can plug this into a charger. Also, what we can do is we can install a battery here. So if we connect the battery pin out to your 5-volt in, there is a 5-volt in also called VSys, and a ground. If we connect the battery to here, then we can use it on battery power as well. Uh,
So is it that this device is able to store some data, or it will be real time?
yes, the Raspberry Pi Pico W, which is the microcontroller, this contains 2 MB of flash memory. So there you can store data, like you can create files, and you can write data into that files, and you can also export them or upload to any cloud. And the sensor is just for sensing data and sending the data to the microcontroller.
Okay, okay.
Any more questions?
Sir, can you show one more time slide number 13?
Yeah, sure. Okay, IMU sensor we are not doing today because of some technical glitches. ESP32 S3.
Multi-channel. Sir, my question is, what is the use of multi-channel gas sensor
Yes.
in while using for air quality index? Okay, okay.
Sensor. Okay, so for multi-channel gas sensor, what it does is it like collects the data for NO2, then carbon monoxide, then VOC, that is volatile organic compounds, and as well as ethyl alcohol, which is C2H5OH. So let's just hop onto Wikipedia for once and let's see the measurement table for air quality index. And for India, what we can see is that NO2 is actually a major pollutant, and we can measure the concentration of NO2 using the multi-channel gas sensor as well as CO. And this is for outdoor. For indoor, VOC, which is volatile organic compound, it is a major player. VOCs are found in your cigarettes, then in agarbattis, and then while you're cooking, there is an increase in VOC levels. So anything organic material, like anything made from carbon, you're burning, VOC concentrations rise, and excessive exposure to VOCs is not good for health. So there also we can measure the amount of VOC for indoor air quality index. Uh, you're not audible. Excuse me.
Carry on. Yes.
Okay. Since when have I been muted? Hello. Uh, till when did you hear? Till when did you hear? Hello.
You are searching for a air quality index.
Yeah. Then after that, the data was not audible, right?
No.
Yes.
Okay. So by mistake, it was muted. So let's go over it once again. The multi-channel gas sensor, it's clear, right? That the multi-channel gas sensor, what gases it measures. I'll just bring up the slide. Yeah. So what we can see is it measures NO2, carbon monoxide, ethyl alcohol, and VOCs. So NO2 and CO, these two are major pollutants for indoor. I mean outdoor as well as indoor. So, and VOC is a major pollutant in indoors because it is emitted from your burning of cigarettes, agarbattis, then cooking oil. So, when you combust these, combust anything like containing carbon, you can get some volatile organic compounds, VOCs. So, these are also cancer causing if inhaled in high concentrations, and so we can use this sensor, multi-channel gas sensor, to measure them as well. Ethyl alcohol can be used to create a portable breathalyzer, which can be used by police forces. And apart from that, NO2 and CO can be used for uh, your indoor as well as outdoor air quality measurement. Does that answer the question? Am I audible?
Yes.
Yes. Yes. Okay. And the question is, the answer is clear now, right? Like, why are we using multi-channel gas sensor for air quality measurements?
So for DHT temperature and humidity, we are using DHT 22 sensor. Can we use
Yeah.
DHT 11 sensor?
Yes, obviously we can use DHT11 sensor. So here only we can just change up DHT22 with DHT11, and we can use this. So is it clear? We can just use DHT11. Currently we don't have a DHT11 sensor, so we will not be able to show the live demo, but replacing just 22 with 11 will work. So should I move on to the next board, like ESP32 S3 Pico? Should I show the interfacing there?
Yes, sir. Yes,
Okay.
sir.
So we are moving on towards the next board, which is ESP32 S3 Pico, which apparently is the better of the two. So let me bring up Tony once again. It is glitching on this screen. Yeah. I'm sorry. Uh, okay. So 32. So let's print hello and see whether it works. Yeah, it's working. So we will now give a demo on DHT sensor on this board, which is ESP32S3. As I said, this is containing more amount of flash memory and RAM. So this can be used to run machine learning algorithms as well. And there are some issues in ping tier. 11. We'll just check the connections once. There's some connection. There are some connection issues. Plus goes to your VBus. VBus connected here. Okay. Minus is ground. Minus is the yellow one, right? Minus is connected here, and pin 11. Pin 11. Okay, this should work. So here we can learn that we have to be careful for selecting our ports. Like for COM22 it was not working, but for COM23, these COM22 COM23 are the IDs of your USB port in your system. So like, and if you're using Linux, it would be dev/tdevice/0 or 1. For Windows it is COM23 COM22. Okay, so any questions regarding this sensor and interfacing,
Sir,
or the issues we just faced? Yeah.
sir, what is the pin 11 in the code DST sensor when initialized?
Yes. There is a. Let me just share my screen. Let me stop sharing because I need to bring up like 1 minute. 1 minute. We share ESP32 S3 in out. When you'll be buying any board, you'll be getting a pinout diagram like this. So in this pinout diagram, what we can see is that there are few pins which are general purpose input output pins. These are called GPIOs. Now GPIOs contain some IDs which do not match with the pin numbers. So your pin 1 contains the GPIO ID 11. So pin 11 refers to the GPIO pin, which is your general purpose input output pin, which you'll be able to see in the pinout diagram which you'll be getting with your board. So this GPIO 11 can be entered into the pin function, like pin constructor, and this specifies that the GPIO 11 pin is being used.
Okay,
So,
sir. So how we consider that which pin we are using, we have to use. There are so many pins.
yeah, for DHT22 this is fine because this is just a digital output. But for there are some protocols with by which some sensors communicate with the microcontroller unit, such as your I2C, UART, and SPI. Now, consider these as suppose languages or the way we should communicate. The way we should communicate, such as your suppose I'm talking to Povitra in Bengali. He understands Bengali. That is why we can communicate with each other. Uh, with someone who can understand Hindi, I can communicate in Hindi. For someone who knows English, we can communicate in English. So these
Okay,
are
sir.
different types of protocol which we should follow. So for that, there are specialized pins
Okay,
which
okay. That means it depends on the device which we are connecting to it.
yes, sensor protocols.
Sensor.
And
Okay.
the sensors come with something called a data sheet. So there the protocols are mentioned.
Okay, sir. Thank you.
Thank you. Uh, should I move to the next sensor?
Yes.
Okay, so the next sensor is a very interesting one, which is the laser dust particle sensor, and it will be first interfaced with PicoW and then with ESP32S3. So like how a laser dust particle sensor works is like we need to measure the concentration of dust in in the surrounding, in the ambient air. So there are a few there are a few classes of dust particles which are your PM10, PM2.5, and PM1. This means let me just enlarge my screen, and we can see that PM means suspended particulate matter in the air, and 10 means 10 micrometers or less. Similarly, 2.5 means 2.5 micrometers or less, and 1 PM1 means 1 micrometer or less. So what this sensor does is it first uses a fan to draw in the ambient air, and then it draws it into a chamber. So now the chamber contains air and some dust particles. Now, a small question for everyone, that is, there are two rooms or two chambers, right? In one chamber, there is no dust particle, and I am shining a light on it. In the second chamber, there is a lot of dust particle, and I am shining a light on it. Light is coming out from the other side of the both the chambers. Which light will be brighter?
So the one with lighter dust particle.
Lesser dust particle.
Lesser dust.
So what we can do is we can use light intensity to measure the concentration of dust particles, right? So here what is happening is we are shining a laser, and then the sample is reflecting the light, and then there is a photon detector here which is measuring the amount of light incident on it, and based on that it is correlating the incident light to the amount of the concentration of dust particles which is present in the environment. I mean, not in the environment, in the chamber, in this chamber. So this is the entire working principle. It is clear, right? So let's move on to this. Let's move on to this interfacing. Here we are using a protocol. I just mentioned protocols, and here we come across our first protocol, which is called UART, Universal Asynchronous Receiver and Transmitter. You need not worry about that huge name, because it just means that there is a transmitter and a receiver, and the transmitter of my sensor is connected to the receiver of my microcontroller, and the receiver of my sensor is connected to the transmitter of the microcontroller. So if we remember this thing, we can interface our devices. And apart from that, there are ground and VCCs for the current flow. And let's see the demo, what data we are getting. We just restart Thorny. And select Raspberry Pi Pico, and then just go to dust demo, because we are demoing dust particles. And we can see that we are able to get the concentration of PM1, PM2.5, and PM10 dust particles. So let's just do that trick where we can see the data via serial plotter. দেখে কথা বলে Let's stop this and start it now. Oh, acha. We have sen017.py in here, right?
Yes.
Okay, so we have to use that. So 1 minute, there is some problem. Can you just, yeah, thank you. And this is the driver of the sensor, and as you can see, the values will be getting stored in here, and we are using I2C and reading. We are using UART and reading the data. And here I have here I have implemented the runner function for this, so we can just use this. Okay, now if we start the serial plotter, let's see what happens. এক minute. Yeah. So blue is the PM1, orange is the PM10, and red is the PM2.5. Acha, orange is the PM1, red is the PM2.5, and brown is the PM10 concentrations. As you can see the data in here. Actually, this serial plotter interprets all the numbers which are getting printed here. So it is basically showing 1.0. 0 is encoded as blue, and it is getting printed in here. So apart from that, this is the variation. And if you can see there's a actually you can see there's a fan in here. Is it visible? This is a fan.
Yes, sir, visible.
Yeah. So what this does is it draws in the air, and here there's a chamber and there are lasers. And like if I just blow into it, the pollution will increase. The dust particles are going to increase. As you can see, the by blowing into it, actually I'm forcing the outside air dust particles inside into this sensor. So we are getting a certain spike in the data. So the similar can be done by using ESP32S3. Just there is one difference, which is just the GPIO ports. So let's move on to the multi-channel gas sensor. Any confusion or any further questions regarding the SPM sensor, the dust particle sensor? Actually, we were going to show a PMS003, but the PMS003 is being used in another project. So we are using SEN0177. The principle is same. Also, the driver logic is same. The both are completely same. The manufacturers are different. PMS003 is manufactured by Plant Tower, whereas SEN0177 is manufactured by DF Robot. So, any further doubt regarding dust particle sensors? Multi-channel. Okay, so let's move on to the next sensor then, which is dust particle. The multi-channel gas sensor. So multi-channel gas sensor, what this does is it measures the concentration of various multiple gases. So what this does is it will be it will be measuring the concentration of gas. And how? So as you can see, where is the multi-channel gas sensor? Can you show me once? Yeah. So there are four square-like things. Can you see this? Are the sensors visible? Yeah. Am I audible? I don't think I'm audible.
Yes, you are
Yes, sir.
audible.
Yes, sir.
Ah,
You are audible.
Yes, sir.
okay. Oh, okay. So are the sensors visible?
So can you please show it again?
Yeah. These squares, are these squares visible?
Yes, sir.
Yeah, these four squares, right? So these measure your NO2, CO, ethyl alcohol, as well as volatile organic compounds. Yeah, thanks, Povitro. Now you can, I think it's more clear. So what these does do is these individually capture, contain a few chemical compounds. Okay. So in each of these boxes, a different chemical reaction occurs, on which there is emittance of some electrons, right? And based on the flow of electrons, what is created? A potential difference. So based on the potential difference, we get a voltage, and from we can measure that voltage to get the your concentration. So that entire thing happens in the circuitry in here. So, and we are getting the we will be getting the concentration. So till Povitra sets up the device, the interfacing. Uh, any doubts till now? Or any other questions regarding like intelligent systems or environment monitoring?
Hello.
Yeah. Yes. Hello.
I have a question actually.
Yes, sir. Yes, sir.
Yeah. So actually, the you are sensing here, to carbon monoxide and all these gases actually.
Yes, sir.
How actually it can be checked regarding the selectivity and specificity of those gases, like whether any other interference or any other gases are not being selected, only they are specifically sensing NO2 or CO.
Yes, sir.
Like
Actually,
what
sir.
principle has been used? Any sort of related to specificity?
No,
For
sir.
an
These are
example, like there are similar kind of gases may be present, might be present. So it has to select only to it should not select or sense any other gases. So how that specificity can be achieved?
Yes, sir. There are two parts to this, sir. So the first part is that the sensor working principle. Since this is a low cost sensor, the
Yeah.
error may arise that interfering gases may cause certain chemical reactions, which also cause emittance of free electrons. So what we, apart from that, what we can do is we can use calibration. Like this is currently this is uncalibrated. This is an uncalibrated sensor just for demo purposes.
No, this is only calibrated by the component.
This is calibrated by the component.
We don't
Yeah.
do any specific calibration on the sensor.
Yeah, currently we are not doing anything, but interfering gases is a concern for low cost sensors. So what will 1 minute? Kyolo. Interfering. Am I audible? Like,
Yes.
yeah, am I in the meeting? Yeah, because the screen suddenly switched. So, yeah.
No,
So
you're audible.
yeah. Based on our research, what we have seen is there are certain methods like soft calibration, where what they are doing is they are using the concentration of other gases, interfering gases, and using some regression machine learning algorithm to create a formula, and based on that formula they are trying to display the correct value of a single gas. Now how will we know the ground truth? For that there are high quality sensors which are costlier, and which are being used by air quality monitoring stations. We can use a method called co-location, which is basically like placing our sensor, asking the permission from the government and placing our sensor near that air quality monitoring station, and whatever values they are showing, that is the ground truth, that is absolute value. So based on that, we can do the pre-calibration of our sensors, and we can perform certain experiments during that pre-calibration as well. We can collect all the data, and after that we can just use that data we have collected to perform
Train
a
the model.
regression. Yes, sir. And
Okay.
get the
Okay.
accurate data.
I got the point. Okay. So right
Yes,
now, actually, it has to be calibrated. It is just for demo purpose. I mean, you have to
yes,
take
sir.
the
This is
real
for
time
demo
data,
purpose.
then it can be used to train the model, right?
Yes, sir. This can be biased by temperature, humidity, and as well as your interfering gases. So, calibration for industrial purposes or for specific purposes, calibration is required. But for general purposes, such as measuring a relative concentration, so that is my NO2 has increased suddenly. For this type of things, we might not need to do calibration if our other factors are static. I mean, almost static.
Okay. Okay. Thank you.
Yes, sir.
Okay. Thank you.
Yeah. Thank you, sir. Let's see the multi-channel gas sensor interfacing on the ESP32S3. So here what we are doing is we are using GPIO 11 and GPIO 12 pins, and we are using another protocol here, which is called I2C, Inter-Integrated Circuit Communication. Here what it is done is each of the sensors contain an address, which suppose you want to talk to me, you need to know my address, and or you need to say that let's meet at your let's meet at Bhubaneswar, and let's talk there, or so we need to know an address. So that address is provided to the microcontroller, and now the microcontroller knows that okay, if I go to this place, we will get some gas data. Apart from that, we are reading the bit stream as usual, and we are collecting the data of the gases. Where can I get that? So the addresses are provided in the data sheet. So let me just restart Thorny, because whenever we are switching, we are actually switching devices instead of switching sensors. We are also switching devices, so we need to restart Thorny. And ESP32, right? Yes. Yeah. So 40 and 39 are actually, are we using 40 and 39 or are we using 11, 12? 11, 12, right? So SDA is 11. SDA is 11. SCL is 12. Okay. So SDA and SCL is actually the clock pulses. Like here, clock does not mean the time. It is basically a pulse of 1 0 1 0 in a periodic fashion. And SDA is where the data is coming. So if we just start this and tell this to measure, we will be able to see constant values, right? So let's just exploit this. Since our breath contains some gases, so let's see what happens. See, the C2H5OH, the CO, and a little bit of NO2 is also changing. It is like from 16, it becomes 17. So NO2 is not changing that much, but C2H5OH, VOC, and CO are mostly changing. And now again they have become constant. So from this we can see that NO2 is not that much high, so like it is livable currently in this room where I am sitting. But suddenly, if I like there are 2-3 cigarettes burning or 2-3 your agarbatti is burning, and like I have asthma or I have dust allergy, so I can create a system now. If I install a buzzer, I can create a system that if my gas concentration is greater than a threshold, it will just it will just beep the buzzer, and it will what it will do is we can get the alert that it is not safe for me to stay here. So using this kind of low cost sensors, we can increase our quality of life. So let's move on to the OLED screen. Or are there any more questions regarding multi-channel gas sensor or some use cases? Or anything? I guess no. So we'll now move into the OLED screen. OLED, also known as organic LED screen, is currently used in a lot of mobile phones. Every mobile phone we are using mostly uses an OLED screen. And OLED screen, the specialty is the black is true black, mean all the pixels are off. What is the specialty in this? If the pixels are off, then there is no power to the pixel. If there is no power to the pixel, that means our battery is being saved. So what we will do is we will we are currently interfacing the SSD 1306 OLED screen. Now, a fun fact: every sensor or every actuator or every electrical component, they contain something called SKU. So SKU is basically this type of number. So this basically, if we say SKU like SSD 1306, we will understand that this is the type of sensor and everything. And if we search SSD 1306 datasheet, we will get all the protocols and wiring configurations and everything for that. Now the display we are using is 19-inch display with a resolution of 128 pixels by 32 pixels. This can be easily used by small portable devices to display some small messages or the current data you are seeing. Instead of using that terminal or the serial monitor as we were seeing earlier, we can use the OLED screen and just we can just show the we can just show that the values, the measurement, yes, the measurement and values. And apart from that, we can use OLED screen to get messages and make small devices. So let's just start the interfacing. We are using this one, right? Okay. So SSD 1306 and which this one contains everything. Like, which one are you using for?
Main. Check the main one. Yes.
Okay.
Okay.
So for main, we are just writing a small piece of code, which is just we are showing a small NIT logo just bouncing around, but the connections are a bit here and there. Which if you can just should I try again? All right. No. Can you please check the connections once? Like I'm using COM23. So if you to COM22, I guess COM22 won't work. Yeah, COM23. Just run. Just check the connections once. Like reconnect if you. The SCL pin is 11 and the SDA pin is 12. SCL 11, SDA 12. Yes, yes. Okay, so this should work, right? The connections are loose. Yeah, the connections are loose. Can you just change up the wires? Change the wires. Other sensors working. Yeah, other sensors are working. Okay, so yeah, others we have shown there is one issue that my laptop has crashed. So ML part hands-on we cannot show, but model selection and the theoretical parts we will be able to show. Any questions? Yeah. Asking questions. Yeah, they're asking questions. I guess. Yeah. Yeah, I guess. Please, no. Okay, there is some issue. There is some unexpected issue. Okay. Meanwhile, this is getting fixed. Let's move on to machine learning, and I hope by the end we can show you a demo on OLED screen. So, are you new to machine learning or okay? We have a hand raising feature in Google, Teams, right? So, those who know about machine learning, can you please raise your hands? Yeah. Okay, two people, right? Okay, so don't worry if like 2, 3, 4, 3, 4. Okay. It's okay. It's fine. It's fine. Yeah, it's fine. So, machine learning is like I'll go totally a very basic part of machine learning. So it's not an issue. So let's say hello to machine learning because machine learning will be helping us to do some more things. So I'll just give a small introduction to what is machine learning. So first is what is learning. We are learning something, right? We are learning new things. So why are we learning something? Why is the machine learning something? Let's answer some questions. Firstly, learning is basically, as per my knowledge, is ability to provide an answer to a new experience based on some previous experience. So suppose like in childhood, we used to like play with scissors. Sometimes like I what let me say from my story, I used to play with scissors, and one day I cut my finger, and then I learned that you need to be safe with scissors. So if I ask a question, should you be safe with scissors? This is a new question for me, and now I have got an answer. Yes, based on my previous experience because I cut my finger. So what is machine learning is ability of a machine to provide some answers. Now, answers here is providing insights on some new data. And how are we providing insights? The machine is making some rules. How are we making some rules? We are making some mathematical function, some graph based on the existing data. And these rules, these methods we are forming, these are called models. So from now on, if I say model, it means that machine has learned something and he has produced some function. And if I input anything into this function, we'll get the insight, we'll get some result based on the previous data. So if we like hop into the nitty-gritties of machine learning, so I guess most of you have played video games. So let me take an example of small data analysis of video games. So suppose there is a machine, and to that machine I provide some data, which are the video games publisher, a video games that video games genre, whether it is a fantasy game or an action adventure game or a shooter game, and the year it was released, and which the video game was popular on which console, such as Minecraft is more popular on PC, whereas Call of Duty is more popular on Xbox, and then the price of that video game. So I take a lot of data on various games and I provide the publisher, and now I ask the machine, can you learn the relation of how the other factors are affecting my video game price? Why should I ask him? Because I want to make a new video game. So based on these parameters, I want to like increase my profit. So then if I give a new details of any game, of my game, I will see that what price should I need to set when I'm launching the game into the market. So price is not a discrete value. By discrete, I mean a categorical value. It is not a category. Price is a continuous data. I can have price 1 rupee. I can have price 100 rupee. I can have price 125 rupee. I can have price 124.9999 rupees. So learning of rules of some numeric continuous value, it is called regression. Meanwhile, in what is classification? It is that I asked the machine that, okay, I'm giving you all the features, even I'm giving you my game price. Tell me what game genre should I make? Like, should I make an action adventure game or should I make a puzzle game? So the machine will not does not have some data called action 0.5. It has action, it has adventure, it has a fixed set of discrete values. So that so the machine gives me, from that set it picks up one data and said that, okay, this is the class, this is the genre you should set for your game to maximize your profit. So that is called a classification problem, because I am classifying my data. So apart from that, I give the machine all the data and say that group it, just group the data based on whatever you feel like. This is done by basically market analysts to analyze the market, like which type of games are similar. So what else should I do? And suppose there is some which type of games are more played, which are type of game are less in number. So this getting insights from grouping, which is done by machine without any other data, like without seeing any other data, is called clustering. So why am I talking about machine learning all of a sudden? So where does machine learning come into play in sensing systems? So for that, let's just go to the 7 layers of IoT once. The first layer is sensing. Sensing, we just had a demo. It is just taking the contextual information from my environment and then creating electrical impulses. And now from sensing, we are doing local processing, which is basically, now from these electrical impulses, we are going towards a microcontroller unit. So the microcontroller unit is being fed the electrical impulses and data. And now we are doing some processing. Suppose, as I said, the example that you have dust allergy and someone is smoking cigarettes, you have this device with a multi-channel gas sensor and dust particle sensor. And what you are doing is you are just turning the device on, and the device will now calculate a threshold that whether your the concentration of gases, the concentration of dust is above a certain threshold. And for that, we are doing a small if level is greater than this. So this is a small processing. So, and we are doing it in locally. By locally, I mean we are not sending this data to some cloud server on over the internet, and there in the cloud server it is getting executed, and then we are fetching the data. We are doing it local in our board only. So it is local processing, and then it is local storage. As someone asked that like, can we just we are seeing the data, or can we store it? We can obviously store it, and we can also store it on an SD card. So this is the local storage. So apart from that, so this is the edge computing. So why are we calling it edge computing? So imagine a cliff. Imagine you're running, and you come to the edge of a cliff, and from the edge of the cliff there are only clouds. You cannot see anything. Okay. So similarly, you have come to the edge of the cliff. You are on land, and now there is only air, which is there are only networks and the internet, and then we'll come to the cloud computing. Okay, so that is why we are at the edge of the network. That is why we call this edge computing. So after that we have the network, which is connecting various devices using wired or wireless medium, and the internet is a huge network, huge public network. Then now after the network we come to fog computing. And why fog? Excuse me. So nowadays we are like experiencing fog, right? So what we have seen is that when we are standing here, and 10 meters away there is my friend. I am not understanding that my friend is here. There is some person there that I can understand. Similarly, in fog computing, there are cloud computers. Like, there are remote computers which are called cloud computers. So we don't know the specifications of the computer. We don't know how the computer feels like, looks like. We just know that we are putting the data on that computer. We are processing the data on that computer. We're storing data on that computer, because our machine, as we said, the storage and the RAM is in megabytes and kilobytes. So we can't store everything. We need a cloud computer, right? We need a remote machine if we want to store huge chunks of data. So for that we are using cloud processing and cloud storage. So this is the fog computing. So why am I telling all this? Acha, any doubt regarding this 7 layers of IoT? Okay, I'm moving on to uh, where does machine learning come into play? So in obviously in local processing, we are taking sensing and we are doing some processing. And in this processing, if we place a machine learning model that I am giving you data, you use whatever you learned from the previous data and give me some insights on whatever data you are getting. This is called local processing. But also we can use cloud processing. Like, I am taking the data and I am sending via the network to a cloud server. And in the cloud server, we are running a larger machine learning model. So in two places we can use machine learning models. And now you have two options. So now the question comes, which option you will choose? So on a remote cloud server we can choose, but there is a problem that it cannot work offline. We need internet. But we are getting higher accuracy since we can execute more complex algorithms, because the RAM is higher, so more computations can be done. And secondly, the storage is more, so larger models can be provided inside the cloud server. But there are cons. As I said, it works offline. We need more network usage, and also more data is going to the cloud. Now, the microcontroller I have with me, I have it in my pocket, or a device in my pocket. That's it. But if I'm putting it into a cloud server, I don't know if the channel is safe or not. I don't know whether that cloud server has been hacked. I don't know whether the company is ethical. So I don't know whether my data is safe with me. So there is a privacy concern. So there, while designing any intelligent system, there is always a question that will you sacrifice privacy to get slightly better results, or would you sacrifice a bit of accuracy to preserve your privacy? So on the edge, we are obviously preserving the privacy, but we cannot fit larger models. So accuracy takes a slight hit. However, it is offline, so no internet connection is required to run the machine learning algorithms. So still we are confused that which one we should use. Actually, there is no absolute answer. It depends on your use case. If you need higher accuracy, then you should obviously go for a cloud server. If you need a slightly low accuracy, is fine. Go for edge. If stable network connection is available, go for cloud server. If stable network connection is not available, you can go for the edge computation, running machine learning on the edge. Also, if privacy is not a concern, you are just giving the NO2 values and CO values, like you're not sending any GPS or any like voice data or pictures, you can send to the cloud server if you want. Otherwise you can use the your you can do computations on the edge if you need your privacy to be protected. So here, unfortunately, we won't be able to show you a demo, but we have a video. The video was shown. No, video was not shown. We have a video. First, we will show you what we have built and already, and we have displayed it in a conference called ICDCN, which took place this year in IIT Madras. So let's start the video. Okay, 2 papers have been published, and let me let me make the video do the talking. Is the audio audio? Like, is it audible? Is the audio audible?
Yes, sir.
Okay, okay. I
Yes.
think it was shown. I think this was shown. So we are actually aiming for a intelligent personal air quality monitoring device. So the device is basically so what it basically does is, first let's see why we need this device. So everyone has a weather app on their phone, right? And you can see the air quality index. So tell me, can you I mean, is the air quality index being shown, is that true for you personally? Is the quality of air around you being shown by your mobile phone?
May not be.
Yeah, it may not be, right? It depends on the city. Like it gives a generalized AQI because there are several air quality monitoring stations, and those are lesser in number. So those are sparsely populated. So what we are getting is generalized air quality data, right? So we need a personal device if we want to monitor our pollution exposure. And actually monitoring our pollution exposure is important because we all are like, I am also suffering from cough. I don't know why I am coughing. It may be because of ambient dust particles. Okay. So also many people are getting asthmatic fits. They don't know why suddenly I'm getting an asthmatic fit. It might be because of some gases which are choking their respiratory tract. So for that, you need to monitor your personal pollution exposure. Also, another thing is you this also shows some insights on your daily habits. Like suppose someone likes to smoke, so they can also see that what is the health impact right? So for this, we need now we have personal monitors, personal air quality monitors. They are available on the market. But the thing is, we have also observed the thing that the sensors, they become faulty after few days. So what should we do for that? Like we should have a system, right? That like we should be knowing, the device should be telling us that the sensor has become faulty. The data you're getting is not up to the mark. So you can check. And also, if my sensor gets faulty, should I throw my entire device away? It will generate e-waste, right? So if I buy a sensor from the market, or the manufacturer sells a specialized sensor, we can just plug it in, and uh, our device is again good to go. So for that, we need two ways in which we can measure the same pollutant. Why is that? Because in the first way, we are just measuring the primary pollutant concentration around us. Second, in the second way, what we are doing is we are using machine learning to estimate the similar concentration. For our current prototype, what we have done is we are just measuring an AQI level from 1 to 6, and we have made a classification problem. So we are showing, like, we are using a dust particle sensor, and we are calculating the real AQI from 1 to 6, and we are just showing we are using some ambient features such as temperature, humidity, then some weather conditions, and some temporal conditions to, like, to use the to show the data, like to classify the ambient AQI using machine learning. So now we have two ways. One, using dust particle sensor, we have got the ambient AQI from 1 to 6, and second is your we have used these machine learning model on these features, and we have got data from 1 to 6. Now what now what we are doing is we are just like now what we are doing is we can compare the data, and if the deviation is a lot, deviation is huge, then we can say that there is something faulty with my primary sensor, which is a dust particle sensor. So this tutorial what I discussed does not it focuses mostly on deploying the machine learning models. So what we have already done is we have prepared a data set for Durgapur city for around a year by making our own data collection box, and we collected these data, which is temperature, humidity, the apparent temperature, the minimum hourly temperature, maximum hourly temperature, the air pressure, wind speed, wind direction, the amount of rainfall, that is precipitation, the cloud coverage, the weather code, that is sunny, hazy, etc., the hour of the day, and the time cluster. What is time cluster? Suppose from morning 10 to 11, it is it is quite busy because people are going to office. After 11, it is a bit the roads are a bit empty. So basically, the dust particles are lesser. Similarly, the month season, these also play an impact on the amount of dust particles in our air, because during the Diwalis there is more dust particle. Also during winter there is more dust particle, because as we have seen, there is a correlation between humidity and temperature. Do we have the no? We don't have the graph in here, but there is a correlation. The lower the humidity, lower the temperature, and higher the humidity, more will be the concentration of dust particles. So taking these features, we train a machine learning model. We tell him that here is your data. You create some classification rule based on a certain algorithm, and the algorithm we have used is a random forest classifier.
So this
It
data has been collected by the device, or it's already available data?
it has been collected by device which we had deployed in 4 places in Durgapur city itself.
Okay. So is the data freely available for public use or not?
Yes, it is freely available. It is available on GitHub.
GitHub. Okay. In the name of
AQAMOHO, Aquamoho. AQUAMOHO. There is a chat feature, right? In Microsoft Teams. Yes. It is actually available for only members, team members. Okay, so what I can do is I can just open the paper. I can open the GitHub and I can just show the repository. This one. Aquamoho. Yes, Aquamoho. I can just show a QR code. QR. I will be sharing this with the representative. They can. I am adding it into the slide. I will be sharing it with the representative if needed. Like, I'll be sharing the link or the slide with the representative. I'm adding the link into the slide. So decision tree. Any more questions regarding the data collection process or the features we have used? Okay, so what we are doing is we are using decision. We are using a random forest. We are actually using an XGBoost on our final model. For the demo, we had prepared a random forest classifier, but unfortunately, the demo is unavailable. The Zorg server is the display server is not working. Post login. So what we are doing is we are using random forest classifier. We were using random forest classifier. So random forest classifier is like a collection of what is a forest? Forest is a collection of trees. Similarly, random forest is a collection of decision tree. Now, decision tree, what is decision tree? Decision tree is a structure like this. So, with based on features, some features, you can see the like take a decision. Suppose we are we can see that the we can see the whether you can survive on a Titanic ship or not. So if you're see in Titanic, what happened? That women and children were evacuated first, so they mostly survived. So as you can see that if you're female, so you have a higher chance of surviving the Titanic rather than male. And also if you're a child and having siblings less than 3, you're surviving, because if there are more siblings, then there will be like a shortage of space in the boat. So this structure of data flow is called a decision tree, and a collection of decision trees is called a random forest. Why are we collecting? Because each decision tree might what we are doing is we are telling each decision tree that learn from a subset of features, not the entire feature. And now we are asking every decision tree that what is your opinion on this data. So after that, whatever is the majority opinion, we are making the classification to that. So another thing what we had done is hyperparameter tuning. Now machine learning algorithms contain some parameters which can be tuned by the programmers. Now, the values of these parameters can be tuned to increase the accuracy of a model, and these are called hyperparameters. Now, what is the problem with hyperparameters is that there is no fixed answer that which value of my hyperparameter will give me a higher accuracy. So we need to tune the hyperparameter values, like set some values, check the accuracy, again set some values, check the accuracy. So doing that manually is a tedious task. What we should do is use grid search. What is grid search? We have a fixed set of values for a certain hyperparameter. We just go through the set of values one by one and place it in the model while training, and we say that this is the see what is the accuracy, and then when we see, then after the grid search is complete, we see which hyperparameter give me the better accuracy. So after that, we had maintained a spreadsheet with some columns and model size, which I can actually show. Okay, some part we can do. Some part of the activity we can do, which is phone. We will be able to select the message. We will be able to select the corresponding your data and machine learning model. Let me just provide the access. Kindly bear with me for 1-2 minutes. I will just provide the access. Till then, is there any questions? Okay, it is on my other account. Till now, is there any questions?
Any questions from the participant end? I think there is no query from their end.
Okay. Okay. Yes, finally. So accuracy is a value from 0.5 to 0 to 1, and let me just clear the conditions. Let me just clear the filter. Yeah. So these two are hyperparameters: NEST, which is N estimators, which is the number of decision trees, and max depth, which is the height of my tree which I will be growing. This is the accuracy, and this is the size of my model. Now, what is my dilemma? Why am I not choosing the most accurate model? My dilemma is that the MicroPython file which I showed in the beginning, this itself is 1.4 MB. And now, as I said, the Raspberry Pi Pico W contains 2 MB of flash memory size. So how much space do we have? 600 of KB, which is 0.6 of MB. So the problem we are facing now is we have to fit everything in 0.6 MB. 0.6 MB. So what I have done is I had already, while training, I had already created this sheet so that I can like measure and store the measurements of my model, and I can just now select greater than, and let's see a baseline accuracy of 60% for argument's sake. And we have got some values. So we have to search 600 KB, right? 628 KB is fine. We can store the model. There is something called pickle. We can use store the model with these hyperparameters and then use that in machine learning, use that in our device. Now what we did was, okay, we don't I apologize, we don't have a demo for this, but just bear with me. What we had done is, the model is a mathematical function, and this tree can be easily represented as an if else function. Like, if my gender is male, then if my age is less than 9.5, then died. Else, if my age is greater than 9.5, sorry, if my age is greater than 9.5, then died. If my age is less than 9.5, if my sibling is less than 3, then survive. So this is how I can use if then in order to create a decision tree. Now I don't have to do anything. I have a library, Python library, which I can call, which is called M2CGen. What M2CGen does is the same thing. It creates if else some if else statements which actually represents the output of my model. Now there is another dilemma, that is, we got an if else statement and a Python file, .py file. We can import that py file. It's okay. But what we have to do is, we have to be careful whether the .py file is also within 600 or 650 kbs or not, because it may be that the raw code is size is greater than 600 kb, because we are writing the model in a whole new different form. So if that is the case, we again have to go to the sheet. We again have to select a model which is slightly smaller than that, but accuracy is more or less same, and we can proceed. Then we can create the firmware, which is using a MicroPython SDK, and this is how the data can be created. So this is it from my side. Any questions?
Thank you. Any queries from the participant end?
Okay, I think we have our OLED screen on. Let's see if that is on. Then it's good news. Yep, and you can see NIT working, like NIT moving, NIT written moving here. Is it visible?
Yes, it is visible.
Okay, so we learned another thing from this, which is the cables quality should be checked. Like, these are some thicker cables which we procured. So after using these thicker cables, thicker jumper wires, we are able to use this. So sometimes the issue may not be with the software. Sometimes the issue may be with the hardware also. So we must check our connections and everything. So thank you everyone for having me in this session. This is it from my side.
Thank you, Arko, for your very your hands, very beautiful presentations as well as your hands-on and your simulations, everything. I hope that all the participants are able to learn a lot of things from your demonstrations. It's really wonderful that your laboratory session. This is our first laboratory sessions, and you did that very good job. I hope that they
Thank you,
are
sir.
able to understand and know a lot of things. Okay, thanks for your valuable time. Okay,
Thank you so much, sir.
so wish you all the best for your upcoming career. Thank you.
Thank you, sir.
Thank you, sir.